one place where we can apply definite integrals is in finding volumes. Now, in this case, we have a tetrahedron. Now, the tetra is for 4 because this is a shape that has 4 triangular faces. And the way I've drawn it, 4 of the faces, the ones that are in the back here, are right triangles. So there's a base that's a right triangle here, and then there are 2 upright sides, and those are both right triangles. And then there's a face in the front of all this that is not necessarily a right triangle. So, okay, so we've got this tetrahedron. Now, notice that if the cross-sectional area of this was always the same, this would be an easy problem because we'd have a prism. So what's happening is, as we go up, if we think about the base, right, if we slice parallel to the base, we see another triangle that is similar in shape, but it's a different size. And so the cross-sections are kind of shrinking as we go up through there. If they were constant, then we'd have this prism. So we'd have a triangular bottom and a triangular top. And then the problem would be easy, because we would just have to take the area of the base, which you could find pretty easily because that area is just 1/2 3 times 6, so that would be 9, and then multiply it by the height. So the volume would be A times H. But because our cross-sections are changing, that's not the case. It's not a prism. It's a little bit harder. But whenever something would be simple, if some quantity was constant, and we have this problem because the quantity that we wish was constant is changing, then what we ought to do is to slice the input for that quantity so that what we wish was constant will actually be roughly constant over some short interval. So this is our plan. Let's partition the interval from 0 to 4 into tiny little slices. Now what that creates are a bunch of, as we break that interval up, right, we have a bunch of triangular regions. If we slice them fairly fine, each slice is kind of a wedge, but it's basically, oops, I need to draw that wedge a little bit better. Okay, so I pull out this one wedge, and it basically, although it does have a little bevel on the edges, for the most part, the difference between the area of the base and the area of the top is pretty small. And so we could find the volume of one slice pretty easily, and then sum up the volumes of all the individual slices, and then we'll be done. So let's see. If we look at an individual slice, let's say this is just, some representative slice we pulled out. I'll call it the ith slice. So it's just completely generic, delta xi. Then I need to multiply that height times the area of the ith base. This is where we need to do a little bit of work to find the area of the ith base. Now I can see that the base here is a triangle, and that it's similar to the triangle that forms this base of the tetrahedron, but it's just a little bit smaller. So let's think about the two sides, because there's still going to be a right angle here. So that base is still going to have a right angle there because it's a similar triangle to the one in the base, which has a right angle there. So it's still going to be a right angle, but it's going to be a different size. So let's think about each side, because we know that the area is going to be 1/2 this length, I'll call it length I, times this width I. So length I times width I. And let's examine those two quantities. First, for the width. The width, if we look at this side here, this side that's standing straight up, it's 4 by 3. So we know that when we're down here with, I'm calling this variable x, so when we're down here with x equals 0, then the width is 3. But by the time x equals 4, the width is 0. So we have this line. Let's see, we need to cook it up so that there's going to be, we can see a linear relationship between our height up through the tetrahedron and our width. So I just need to figure out what that width is. And okay, then there's some intercept b. Okay, well, we have these 2 points. We know that when x is 0, then m times the, let's see, then we know the width is going to be 3, right? So this gives us one equation. 0 equals m times 3 plus b. The other thing we know is that when x is 4, m times w plus b is going to be, oh, let's see, the width is going to be 0, huh? So this equation tells me that b equals 4. And now knowing that b is 4, this other equation tells me that the slope is negative 4/3. So we have this relationship here between how high we are through the tetrahedron and what the width is. The width is going to be 4 minus 4/3, or xi is going to be 4 minus 4/3 the width. Let me check that again. Let's see. When the width is 3, then that's when x is 0. Good. And when the width is 0, that's when x is 4. Now actually I want the width as a function of x, so xi minus 4 is going to be negative 4/3 wi. If I multiply through by negative 3/4, I get negative 3/4 xi, and negative 3/4 times 4 would be positive 3. That's the width. Okay, that makes sense. When x is 0, then we have a width of 3, and when x is 4, then we have a width of 0. Let's do the same thing. Now we know the width in terms of our height up through the tetrahedron. Let's do the same thing for the length. So to get the length, let's look at this face that's back on the back, this other vertical face. Now looking at that vertical face, we can see it's got a length of 6 and a height of 4, and we're going to think about what's the length if we're at some slice at location x. Here we want to know what's the length that goes along with that. Okay, but again, it's a linear relationship, so we know the length, the ith length is some slope m times the ith height, right, plus some constant b. And we can do what we did before. We can see that when x is 0, then the length has to be 6. So plugging that in, it tells us that 6 is equal to m times 0 plus b, so in other words, b is equal to 6. Now we know that b is 6, we can figure out, we can use this other point that we have. We know when the height is 4, then the length should be 0. So we'd have 0 equals m times 4. When the height is 4, the length is 0, and we know that b is 6. And this lets us solve for m. This tells us that m is negative 6 over 4, or that's better known as negative 3/2. Okay, so now we have an equation for our ith length as well. L sub I is equal to m, which we just found out was negative 3/2, times the height in the tetrahedron, plus b, which is 6. Great. So that when x is equal to 4, yeah, we have a length of 0, and when x is equal to 0, we have a length of 6. Perfect. Okay, so that's our length. Our width we already calculated was negative 3/4 xi plus 3. So now we can find a sub I, the area of the ith face, by taking 1/2 times negative 3/2 x sub I plus 6 times negative 3/4 x sub I plus 3. And once we have a sub I, we can actually find the ith volume. So v sub I is equal to 1/2 times the area of the face, negative 3/2 x sub I plus 6, times negative 3/4 x sub I plus 3, times the thickness, which is delta xi. So we're just assuming that one little slice is basically a prism, so we can take the area of the base times the height to get the volume. And that's true if our slice is really thin. Now, I'm actually running out of space, so I'll copy this formula for the ith volume over to the next slide where I can write a little bit. So here's our formula. The volume is the area of the base, which is 1/2 the base times the height, because the base is a triangle, times the thickness. What we want to do is to get the total volume, we want to sum up from the very first slice to the very top slice 1/2 of negative 3/2 xi plus 6 times negative 3/4 xi plus 3 delta xi, and that will be a good approximation to the volume. And then to make our approximation perfect, we're going to take the limit as the norm of the partition tends to 0. Of course, that's the limit of Riemann sum, which is the definite integral. The interval we partitioned was from a height of 0 up to a height of 4, so we have the integral from 0 to 4. And then we have 1/2 of negative 3/2 x plus 6 times negative 3/4 x plus 3 dx. Now, in order to integrate this, probably the easiest thing to do would be to multiply all this out. I'm gonna pull out my constant 1/2 just so I can get it cleared out of the way at first. Then if I multiply these together, negative 3/2 times negative 3/4 is positive 9/8 x squared. Then we have negative 3/2 x times 3 would be negative 9/2 x. And then we have another negative 9/2 x would make negative 9x. And then we have 6 times 3, which is 18 dx. Okay, so we just have to find an antiderivative. Since this is a nice polynomial, it's continuous. So the fundamental theorem says we'll just find an antiderivative of this thing. So an antiderivative would be 3/8 x cubed minus 9/2 x squared and plus 18x, and we just have to evaluate that antiderivative between the two bounds, between 0 and 4. So we have, if we plug in 4, we have 4 cubed, that's 64, but 64 divided by 8 is 8, and 3 times 8 is 24, so we have 24. Put a 4 here, we have 16, but half of 16 is 8. 9 times 8 is 72, so we have 24 minus 72. And then we have 4 times 18, which is actually 72 as well, minus 1/2 times, well, when we plug in 0, we get 0 minus 0 plus 0, so that really doesn't matter in this particular case. So we have 1/2 of 24. 72's cancel, and so we have a volume of 12. The volume is 12. Now, you probably already know that for a volume of a pyramid like this, so for any pyramid, you just take the area of the base. In this case, the area of the base is 1/2 the 3 times 6, so that's 9 times 1/3 times the height. So you take 1/3 of 9 times the height, which is 4, and you get 3 times 4, which is 12. So our result that we found by integrating actually agrees nicely with the formula that we've seen before from just basic geometry.